Welcome back, my Algebra 2 students. We are talking about Lesson 34 today, more uniform motion problems. Now, we are comfortable at this point using uniform distance, and that just means that distance of 1 equals the distance of 2, right? That's where we have a problem that looks like this. Mom is going to Grandma's house, and then Grandma's coming back. And it's the same distance. So distance 1 equals distance 2, right? And then we turn that into the rate of 1 times the time of 1 equals the rate of 2 times the time of 2. We're comfortable working those. We can pull the information from a word problem and sub in and solve this. We're also fairly comfortable with combined distances, and that's where we have d1 plus d2 equals some distance x that we're given, and those problems look like this. So-and-so went this way, and then so-and-so started driving and went this way at a different speed, and the total was x. The total distance was this. So we know we can turn those into the rate of 1 times the time of 1 plus the rate of 2 times the time of 2 equals x, and be able to pull variable information and fill it into these categories or into these variables and solve to find the missing variable information. We're pretty confident with those. So now we're going to talk about a different one, a different type of uniform motion, and that is where we have a difference in the distance, or it's not a combination. It's where we have a situation where so-and-so, number 1, person A, goes this distance, and they get there by a certain time. Let me change my arrow to right there, right? And then person number 2 goes within so many feet or miles or kilometers. Maybe they're 40 kilometers shy of being where that person is. Maybe the time is the same and they're slower. Maybe they left at a different time, so they can't travel and make up the distance or the difference in the distance by a certain time. Or for whatever reason, they didn't go as far. We have to account for the difference in those two distances somehow. And typically what we'll do in that regard is we'll say that the distance of 1 plus some unknown distance equals the distance of the other person. Or actually, in this scenario, the distance of 1 equals the distance of the other guy plus 40. Because that's what we have here. But it would be plus some unknown distance to make these two equal and make it an equation. And that is the whole purpose of the equation. You have to find that difference in order to balance it so that they're both the same. And then we would turn around and we would say, because we know we can turn this into rate times time, we would say the rate of 1 times the time of 1 equals the rate of 2 times the time of 2 plus that unknown distance, so that we can make it all equal. So that's what we're going to be doing next. We're going to be doing a problem like that, where we are applying this formula where there is some difference between the two distances that were traveled. Okay, so I'm going to go ahead and write this down. And then I want you to, you can pause if you need to do that. I'm going to clear the page. And then we'll start our first problem like that. And here's our problem. This is 34.1. My book is overlapping the whole thing here. Okay. So 34.1. Millicent began the journey at 6 a.m. So let's draw our little figure here. Millicent, 6 a.m. She begins her journey and she's going 50 kilometers an hour, right? She gets to this point at some point, right? That's where she is. Bo began to chase her, and he didn't leave until 10 a.m. That's when he left. And he's traveling at 60 kilometers an hour. But he never catches up with her. We just want to know what time it was when he got to the 40 kilometers away from Millicent. He got within 40 kilometers of her. So that literally means he's 40 kilometers away, right? So we have two unequal distances. And we're going to start by making our chart. We're going to start with Millicent, and then we're going to put Bo, and we're going to put in our rate and our time. Okay, so Millicent, she began, it doesn't matter what time she began, what matters is that she was moving at 50 kilometers an hour. So we'll put 50 in for her. And then when Bo began to chase her, he chased her at 60 kilometers an hour. We don't know what time it was, how long he traveled, so we could just put the time of Bo in here. But we do know that Millicent started 4 hours before he did. So that's where this matters. The time of Bo plus 4, because she started at 6, he started at 10, she has 4 hours on him. So her time is the time of Bo plus 4 hours, because she has more time invested in this journey. Now, we have this information here already. So now we need to substitute this into the distance equation and solve for TB. So first of all, let's look at Millicent. Millicent, we have her rate and her time. We know what that is. So Millicent is going to be 50. It's her rate. And her time is the time of Bo plus 4 hours. And she has the longest distance. So we don't add anything to her. Okay? Bo is the one. We have his rate. We don't know his time, so we just put in the variable. But he is 40 kilometers away from her. So we have to add 40 to his total so that each one of them are equal. All right? That's this illustration here. He's 40 away. So to make these two equal, we have to add 40 to his distance. Now we can solve the problem. So let's do our distribution. We have 50 times TB plus 200 equals 60 times TB plus 40. So I am going to move the 50 over here. I'm going to subtract 50 from both sides. And then I'm going to subtract 40. Just because I like to have my variable positive. So this cancels and this cancels. So I have 160 equals 10 TB. So when I divide, 16 is the time of Bo. So that means he traveled for 16 hours. Now, what time was it when Bo got within 40 kilometers? He started at 10 a.m., right? So 10 a.m. We know that 12 hours later, so plus 12 hours is going to equal 10 p.m., right? So that flips it. So we have 16 hours left. So at 10 p.m., if we add 4 hours, I'm sorry, did I say 6 hours? We have 16 minus 12. We have 4 hours left. If we add 4 hours to 10 p.m., that's going to equal 2 a.m. So it was 2 a.m. when he got within 40 kilometers of Millicent. So it's not enough just to find the missing variable. You have to figure out what are they asking for. And in this case, it was time. So we figured out the hours but you started his time and we added it in until we figured out what time it was that he got right here. Okay? All right, so let's do 34.2. Take notes if you need to. Pause, do that. I'm going to clear the page. All right, and I'm going to go ahead and pause it and type this in because that's way better, way better than my handwriting. So hang on just a second. All right. It looks so much neater when it's typed instead of handwritten by me. Let's do 34.2. When the sheriff began his pursuit, Robin Hood was already 7 miles out of Nottingham. All right, that's our diagram. We don't know, how or when he got there. We just know that he's already 7 miles away from the sheriff. And this is Robin Hood. And this is the sheriff. So he has 7 miles on the sheriff, right? If the sheriff traveled at 6 miles per hour, while Robin Hood's rate was 2.5 miles per hour, how long did it take the sheriff to catch up? So let's do our chart. Remember, this chart is all about distance. This is the one about rate and time. So this is where we sort that out. Rate and time. And this is Robin Hood, and this is the sheriff. All right, so Robin Hood's rate was 2.5. I'm going to write it like a fraction just because I can. 2.5 miles per hour. And the sheriff traveled at 6 miles per hour. We don't know how long it took them yet, but we know that they both started at the same time. He was already, that word already, that's our key. He was already 7 miles out of Nottingham, and he started traveling at the same time that the sheriff did. So their time is equal. So the time of the sheriff is equal to the time of Robin Hood. We just don't know what it is yet. So what that means is we can substitute in one for the other. So we could say TR and TR because they're the same, right? So how long did it take the sheriff to catch up? So now we have to figure that out. So let's write our problem. So we know that Robin Hood's rate is 2.5 times TR, and he's already 7 miles ahead of the sheriff. The sheriff is 6 miles per hour, and he has the same time, right? Times his time, because they started and stopped together. So let us, and we know they started and stopped together because the sheriff caught up to him. When he caught up to him, the time stopped at that moment for both of them. So you have to learn how to understand what that means when you read that. When somebody catches up to you, your time stops. It's like playing freeze tag. When they touch you, it's the same moment. So we have to think of it like that. So here's our problem. Now we can solve this. So we say, let me make sure I have that. Excuse me. We say in algebra we don't like improper fractions, so we're going to put that into, or we don't like mixed numbers, we like improper fractions, so let's put that into an improper fraction. So 5 over 2 times TR plus 7 equals 6 times TR. So we're just going to move this over, subtract 5 over 2 TR from both sides. And that leaves 7 here. And this is going to require that we do a little bit of math. So we want to put it over 2. So this is going to end up being 12 over 2. That equals 6. Minus 5 over 2. So 12 minus 5, that's going to be 7 over 2 times the rate of Robin, right? So now we have to undo this. And the way that we undo this is by multiplying by the reciprocal. And so that's going to be multiplying this times 2 over 7, and this times 2 over 7. So this ends up being 14 over 7 equals TR. When we divide, 2 is the rate of Robin, which means that they were both traveling for 2 hours. So it took the sheriff 2 hours to catch up. All right, it's a little bit convoluted. It's a little bit sideways. I kind of wrote a little crooked. I think it's because I've got my tablet twisted. There we go, that's better. So that's how we would solve one of these where they don't start at the same place. You just put the addition on the front instead of on the back. All right? Still pretty easy. The hardest part is always going to be figuring out the equation to start with. The rest of it is just like normal. You just use the variables. Understanding how to put that information together. Understanding that their time is the same because they began at the same moment and they ended at the same moment. That's important. You gotta learn how to see that in when they catch up to one another. That always means that it ends at the same time. So that's a phrase when it says catch up, they end at the same time. So that's something that you can remember. Catch up means ends at same time. And when you see the word already, they were already here, that's a clue that they're starting at the same time. Okay? Already means start at the same time. So their time is then going to be equal to one another. So then you just pick whichever one you want to use and put it in both of the squares so that you have the same variable to solve with. Okay? All right. That is all we have for lesson 34. I'll see you guys in lesson 35.